Good morning. So this is our 23rd lecture. In the previous lecture we have specifically discussed about the Sock expansion theory, and if you do remember, majority of the things what we have done earlier, these were particularly related to actually external flow conditions. Okay, so for internal flow we have talked about relay flow and phenol-line flow, but that was also basically happening through a constant area duct. Okay, so till this moment we have not included any case where we are having actually variation of its cross-sectional area. Okay, so now we will start our discussion particularly for the quasi one-dimensional flows. Okay, so quasi one dimensional flows are very important for many things. For example, in gas turbine engines, in rocket engines, in wind tunnels, supersonic wind tunnels, we have actually this approximation which is applicable. Okay, so as a whole, if we see, in general case, we can say that if I have, say, any variable cross section duct. Okay, so say at this point I have area A1, at this point I have area A2, and in between actually if I see, so I will be having some area as function of x if my x is starting along this direction. Okay, so in this situation what we have basically we are having variation of area. So if any fluid is flowing inside this duct, so this duct, that particular fluid has to actually go through this whole process of change in its direction, and it has to follow basically the boundary of this surface. So say fluid streamlines will be something like this. Okay, so in this type of situation, if you see, our flow, if we consider, flow will be having actually two-dimensional or three-dimensional nature depending upon the localized effects. Okay, so if you see locally, there will be some change in velocity. Say if at this point velocity is in this direction, so this velocity will be having certain x component, certain y component, and if this is a three-dimensional structure, then if I take this at some angular location, so there you may find that it is having some other component also. Okay, so locally if I see, locally my flow parameters will be such that this flow condition is nothing but two-dimensional or three-dimensional. So for a square duct it will be two-dimensional, for a even for a square duct, because side wall effects will come, so then it will be a three-dimensional situation. Okay, but what we can do, we can impose one approximation over here. Say if I am not interested in variation of velocity, this localized velocity. Okay, I am interested in defining the average property at any cross section. So say this is the cross section. At this cross section if I consider V average, okay, and say every cross section if I consider V average, so I will be having over here say V average 1, here I will be having V average 2. So what I am trying to do, I am trying to look at nothing but the cross sectional averaged properties. Okay, so if I what I do, if I just avoid the variation of localized effects, and if I simply consider the variation of property, and that property if I consider as area averaged property. So what will be happening ultimately for each and every cross section, say this is an arbitrary any cross section, at this entire cross section I can define some area average velocity, I can define some area average pressure, I can define some area average density. So if I consider these average properties, then what will be happening actually, I can say that in this type of situation my parameter is having unique value at any cross section, which is represented by this average number, and after this whenever I will be moving to new cross section, so here I will be having some new average parameter. Okay, so average magnitude will change, but ultimately in other directions my variation will diminish, and I will be having variation of this cross sectional average parameter across the length. Okay, because across this length my area is changing. So what I can do, if I assume this type of situation, so in this type of situation I am having area A of x, area is varying, okay, I have variable area, and the way I have considered this averaged flow situation, for this averaged flow situation I can say if my density is there, so density is nothing but function of x, because area is changing along the x, so the area average property will also change along the x. Then I can say that my pressure is also say function of x, temperature is also say function of x. So likewise all the properties I can define solely as function of x only. Okay, so this type of situation is called as nothing but quasi one dimensional flow. So what we are saying over here, we are saying over here that though we have variation, but if we define cross sectional average property, then I will be finding that at each cross section I have a unique magnitude of the property, and that property is varying only along the x direction. Okay, while we are imposing this condition, we have to remember that we are talking about compressible flow situation. So in all the cases we are considering the inviscid flow situation. So whenever we impose inviscid situation, then considering this average property at entire cross section is a good approximation. Okay, so it's a good approximation. So considering this, I can reasonably, with reasonable accuracy, I can actually consider that my flow can be considered sort of one dimensional flow situation. Okay, so now if you see all the parameters are varying only in one dimensional, so I can say one dimensional flow, but as it is not a purely one dimensional flow, this one dimensional flow is coming because of this approximation of averaged quantities at each and every cross section. That is why we refer this to as nothing but the quasi one dimensional flow. Is this point clear? Now when we will be talking about the quasi one dimensional flows, first we have to see that how our governing equation takes the form. Okay, so we have started initially with the integral form of the equation, so we will try to apply over here the integral form of equation and then deduce the conservation equations for this, and then we also will try to see one important relation which is known as area velocity relation. So basically area velocity relation gives us the variation of velocity with area. Okay, so when area is changing, how velocity is actually changing with change in area for different flow situations. So these are the fundamental basis for studying this compressible flow through variable cross sections. Okay, so and ultimate applications we will be finding in say rocket engines, gas turbine engines, and supersonic wind tunnel. So let's first try to see that how governing equations behave for this. So say I have a situation that say this is my duct. Here I have station 1, here I have station 2. So this is nothing but inlet and outlet of a duct. Say at this point area is A1, at this point area is A2, and along this I have A as function of x. So if any fluid is flowing inside this, I can consider a fluid control volume as represented by this dashed green line. Okay, so whatever is the shape of this duct, same I can consider nothing but as a fluid control volume. So this dashed green line over here nothing but represents the control volume of the fluid. Okay, so if I see in this control volume, what will be happening, this particular control volume is will be having some P1 pressure, V1 velocity, ρ1 density, and T1 temperature say at inlet point, and similar parameters at outlet will be say P2, V2, ρ2, and T2. Okay, so now considering the fact that how conservation equations can be applied for this, so that will give us the relationship in between parameters at 1 and parameters at 2. Okay, so if I see my continuity equation, I know that my continued integral form of continuity equation is del rho plus, so this I will be representing as V bar, volume integral. Okay, plus rho V vector dot ds vector. Okay, so this is nothing but my continuity equation, this equal to 0. Now if I have to write this equation for what are the assumptions for compressible flow analysis? First assumption we are considering is steady flow. Second assumption we are considering as inviscid flow. Okay. Third assumption we will be considering that negligible body force. So body force of the fluid we will be considering negligible. Okay, so these are the three different assumptions which we will be imposing. So at the moment, if you see what I have inviscid and negligible body force parameters will come nothing but in our momentum equation. So at the moment, if I impose the assumption of steady flow condition, then this integral will be becoming equal to 0. So del rho by del t will become 0. Okay. So ultimately I have to calculate this integral. So if I calculate this surface integral of v vector dot ds vector, first it will be coming at face A. So I have to consider all the faces of this control volume. So at face A, if you see, this is v1 velocity and area vector will be outward normal. So both are opposite to each other. So dot product of v dot ds will become minus v1 a1. Okay, and density at this point is rho 1. So what I can say that surface integral of rho dot v dot s vector will be equal to rho 1 a1 v1 with negative sign. Okay, then plus if I take the second one here, v also is in this direction and area is also in outward normal same direction. So cos of 0 will be becoming a2 v2. Okay, so it is having plus sign, and then I have this area of the control volume. So if you see in this area of the control volume, if you see a streamline, so streamline will be parallel to surface. So this will be my direction of velocity and this will be my direction of the area. Okay, so this is area vector and this is velocity vector over here, and angle between the two over here will be 90 degrees. So for this particular control surface and this particular control surface, I will be finding that in between velocity and area I will be having 90 degrees angle, and because of this VDS will actually vanish over here and I will be getting plus 0. Okay, so this is equal to 0. So from here I am simply getting rho 1 a1 v1 equal to rho 2 a2 v2. Okay, let me make the difference with reference to our complete one dimensional flow situation. So for complete one dimensional flow situation, a1 was equal to a2. Okay, while we have studied the one dimensional normal shock wave. So there I can write my continuity equation rho 1 v1 equal to rho 2 v2. So that was possible when flow is completely one dimensional. When it is quasi one dimensional, then I have to consider rho 1 a1 v1 equal to rho 2 a2 v2. Is this point clear? Then second is our momentum equation. So in momentum equation, if I impose the steady assumption, then del by del t term will vanish. Okay, so now I will be taking the term only which is involving advection. So that term is, can you tell me? Okay, this will be equal to, I have to only consider pressure force. Body force is negligible, viscous force is negligible. So minus integral of, okay. So now tell me left hand side. In the left hand side, rho VDS just now we have calculated over here. So it will be minus rho 1 A1 V1, and then I have this V vector also over here. Okay, so if this V vector, if you see on this face, it is pointed in positive direction. Okay, so it will be V1. So I can write rho 1 A1 V1 square plus rho 2 a2 v2 multiplied with v vector once again in positive direction, so v2 square. Is this point clear? And then vds product For other two control surfaces is 0, so that's why I need not to write that over here. Okay, because VDS is 0 for other two faces. Now let's come to pressure. So I have a minus sign outside, and then I have integral of PDS. So now pressure is a scalar quantity. So say at phase 1 pressure is P1, fine. Then ds, area vector is pointing in the negative direction. So I will write over here minus A1. Okay, plus P2 into A2. Okay, and then I have another important parameter. Now I have some pressure which is acting on these boundaries also. So here also I will be having P pressure. Okay, and ds vector will be something like this away from this. So in this P and ds I will be finding that here I will be having, and I don't know the variation of pressure across this line. How pressure is varying across this line, that is something which is not known to me. So means I know that some pressure is acting on this, but how pressure is varying with this area, that is something which say at the moment I am not knowing. So what I can do, at any point I can actually consider that integration of pressure into dA, and this area is varying from A1 to A2. Okay, so if you see, at any point I am considering P into dA, and the limits of integration are from A1 point to A2 point. So basically I will be considering this projected area on which my pressure is actually acting. So what is the contribution of that? Is this one clear? So that is the reason I have included PDA from A1 to A2. Okay, so if you just simplify this, so it will be becoming P1 A1 plus rho 1 A1 V1 square plus integral A1 to A2 PdA equal to P2 A2 plus rho 2 A2 V2 square. So this is your momentum equation. Fine. Now if you make the distinction from the momentum equation which we have studied earlier for pure 1D flow, so for pure 1D flow momentum equation was P1 plus rho 1 V1 square equal to P2 plus rho 2 V2 square, because first thing is A1 is equal to A2, so that's why this integration will be equal to 0, and this area will be cancelling out. So this was for pure 1D flow. Okay. Now let's come to energy equation. So for energy equation, what will be happening? Can you tell me? So if I take the steady condition, then I will remove time term. So I will consider the second term of energy equation, which is rho v vector dot ds vector. This makes my mass, advection of mass, and then along with this some energy will be going, that is u plus by 2. This will be equal to, because viscous heat generation and all other effects I am neglecting, so I will be having only effect of pressure. So P into V vector dot ds vector. Okay, this is my flow work. Fine. So now this first, as I have already written, first part minus rho 1 A1 V1 times U1 plus V1 square by 2 plus rho 2 A2 V2 times U2 plus V2 square by 2, fine, plus 0, that will be equal to minus, then I will be having P1 into VDS for left face is minus A1 V1 minus of P2, and VDS for right face will be A2 V2. Fine. So I will get my equation as P1 A1 V1 plus rho 1 A1 V1 into U1 plus V1 square by 2 equal to P2 A2 V2 plus rho 2 A2 V2 into U2 plus V2 square by 2. Is this point clear? So now if I take rho 1 A1 V1 as common, inside I will be getting U1 plus V1 square by 2 plus P1 by rho 1, and that will be equal to rho 2 A2 V2 times U2 plus V2 square by 2 plus P2 by rho 2. Okay, so from continuity equation, rho 1 A1 V1 is equal to rho 2 A2 V2. So these two will be cancelling out. Just a moment, there is some issue. Yeah, now it's working. So is this point clear? Now this will be cancelling out. So, and U1 plus P1 by rho 1 I can write H1 plus V1 square by 2 equal to H2 plus so this is my energy equation, and if you see, energy equation over here is actually matching well with the energy equation for pure one dimensional flow. Okay, so energy equation is remaining exactly the same. Fine. Is this one clear? Now can you just tell me one thing, when I have taken these terms in the momentum in the energy equation on right hand side, if you see in momentum equation I have taken these two phases also. In energy equation, why I have not taken? Because here I am getting V dot ds vector. So for this phases, V and ds vector are at a 90-degree angle. So that's why these are actually becoming 0. Is this point clear? So in case of momentum equation, only PDS was there. So that's why this integration is becoming important only for the momentum equation. Okay, but for energy equation, once again I am getting V vector dot ds vector with the pressure, so which is identical to which is making this 90-degree angle, and this product is 0. Fine. Is this point clear? Okay, so I have got these three equations. Okay, so let me write these three equations, because first is rho 1 A1 V2 V1 equal to rho 2 A2 V2. Second is P1 A1 plus rho 1 A1 V1 square plus integral A1 to A2 PdA equal to plus, fine. And third one is H1 plus V1 square by 2 equal to H2 plus. Okay, so now from first equation I can simply say that rho AV is equal to constant. Is this one clear? Can I say rho AV is equal to constant? And from the third equation I can say that H plus V square by 2 is equal to constant. So if this is the case, then from first equation I can also say that d of rho AV will be equal to 0. Fine. D of rho AV will be equal to 0, and from third equation I can say that d of H plus v square by 2 will be equal to 0. So from here I can get dH plus v dv equal to 0. Is this point clear? Is this point clear? So if I have to write in differential form, then I can say that differential of rho a v equal to 0 is valid for continuity equation, and differential of h plus v square by 2 is equal to 0 is valid for energy equation, and ultimately this gives me dh plus v dv equal to 0. Is this point clear? Okay. So what about momentum equation? So if I have to write down the momentum equation in differential form, it is actually including this integration. Okay. So then I have to consider a differential element, and let's consider through this differential element I have, this is my differential element, and say through this differential element I have here pressure P, okay, area A, density rho. Now say this change is dx, this is my differential element having thickness dx. So on the other side say I have pressure P plus dp, area A plus dA, and density say I should not write here direction for density. So say density I have as rho plus d rho. This I can write. So if I take this differential element, for this differential element if I need to write down the momentum equation, I can write that P into A. So if you see P1 A1, so on left side I have P into A plus rho 1 A V square. So in place of rho 1 rho A and V square. So if say velocity is V over here, here it is V plus dV. Okay. Then I can write plus P into dA. So area change through this is nothing but dA only. So this integration I can write as P into dA in place of integration, because integration is if I include the complete finite control surface. Here I am only considering the differential control surface. So then it will be PdA. This will be equal to pressure on other side is P plus, and area is A plus, fine, plus density on other side is into A plus dA into V plus dV whole square. Okay. So let's expand this equation. So if I expand this equation, left and right remains the same, PA plus rho A V square plus PdA, and here it will be becoming P into A, first term, PA plus, then P is multiplying with dA will form P dA, then dP multiplying with A will become AdP, and then I will be having dP into dA. So as dA is small, dP is small, so product of these two I can actually neglect. Okay. Then I will be having plus rho A plus rho dA, fine. Then rho A, rho dA, what else? A d rho, then d rho dA I will be once again making equal to 0. Okay. So these three quantities which I have written now in square bracket. So these I have written in square bracket. These will further get multiplied with V plus dV whole square. So that is V square plus 2V dV plus dV square. dV square due to its small magnitude once again I can actually neglect. So this I can neglect. Okay. So ultimately let me cancel out some of the terms. If you see PA is cancelling out. PA is cancelling out. Anything else is cancelling out? PDA is cancelling out. Okay. PDA has also cancelled out. Let me write then other terms. So on the left hand side I am left with rho A V square. So say left hand side I have rho A V square, and that is equal to ADP plus this rho A will get multiplied with V square. So it will become rho A V square. What will be the next term? Please tell me. Rho A V square plus 2 rho A V dV, 2 rho A V dV, then rho V square dA, 2 rho AV, sorry, rho V square dA, and then 2 rho. So this will be 0 because dA and dV are multiplying, and here also d rho and dA will be multiplying, so this will be also 0. Okay, then I have third term as AV square d rho. So remember that all the terms which are becoming either multiplication of two infinitesimally small value, that I am keeping equal to 0, and if anything is becoming square of very small value, that is also I am keeping equal to 0. So up to this it is fine. Then if you say this rho A V square will cancel out, and ultimately I will get that ADP plus 2 rho AV dV plus rho V square dA plus AV square d rho equal to 0. Okay. Say this is equation number 4. This is my equation number 4. Okay. Now I have one equation over here which is continuity equation, which tells that d of rho AV equal to 0. So if I take this differential, if I expand this differential, this is my continuity equation. So from continuity equation I will get AV into d rho, fine, AV into d of rho plus rho A into d of V, fine, plus rho V into d of A. This is equal to 0. Now let us multiply, this is say if my equation number 5, let us multiply equation 5 with V. So if I multiply equation 5 with V, what I get? AV square d rho plus rho AV dV plus rho V square dA equal to 0. Is this one clear? So say this is my equation number 6. Now what I will do 4 minus 6. If I do equation 4 minus 6, what I will get? A V square d rho will cancel. So say this term and this term will cancel. Then rho AV dV and 2 rho AV dV. So this minus this will become 1 rho AV dV. Fine. This is 1 rho AV dV. Then this term and this term are taken care of. Then I have this rho V square dA. So these will be cancelling out. I will be left with plus, that is equal to 0. So AA will also cancel, and from here I can simply say that dP by rho equal to minus of V into dV. Okay. So this is another important equation in the differential form which relates nothing but our pressure and density. Fine. So this is representing relating pressure, density and velocity. So this is also one important relation between pressure, density and velocity. This is in differential form. Is this one clear? So it means that in differential form, if I have to do, this is my one important relation, that is continuity equation. Then I have second important relation, this is my energy equation, and then by manipulation of momentum and continuity equation, I have got a relation in between pressure, density and velocity. Okay, so all these relations are nothing but available, all these relations are available in the form of, these are available in the form of differential form. Okay, now we have an important, so this is all about the governing equations for this type of flow. Now if I have to determine actually the important aspect which is called as area velocity relation, this is the main foundation of this particular system, area velocity relation. Okay, so if I start with continuity equation, then I know that rho AV is equal to constant. If I take log of this on both sides, so ln of rho plus ln of A plus ln of V will be equal to ln of constant. And now if I take differential, I will get d rho by rho plus dA by A plus dV by V is equal to 0. Okay, so say this is one important equation, say equation number 7. Fine. Now my interest is to find out this parameter d rho by rho, because this dA by A, and we want to find out the relation in between area and velocity. So my interest is to find out this value d rho by rho. So what I can do, I can write this value d rho by rho as nothing but equal to, say, this is my one important relation. So let me use this relation first. So I have seen one relation that dP by, please let me write P and rho correctly. Yeah. So this is dP by rho from the previous slide. dP by rho is equal to minus VdV. So now what I want to do, I want to replace this pressure term, this rho by rho term in terms of velocity. And just now I have seen that in terms of pressure and density I have some relation. Okay, so what I will do, this d rho by rho I will try to write in the form of, say, dP by d rho into d rho by rho. Is it correct? If I write d rho by rho, so then no, this is not correct. First let me start with dP by rho only. So if I write dP by rho, so dP by rho let me write as nothing but dP by d rho into d rho by rho. This I can write. So now rho by rho will be cancelling out. Okay, and this is ultimately equal to nothing but minus of V times d. dP by rho just now we have calculated in the previous slide that it is equal to minus of V into dV. Okay, now if you see this particular, we are writing change in pressure per unit change in density. Okay, so if you see this process over here, when we are considering flow through a variable area duct, so for flow through a variable area duct we are considering complete inviscid situation. So it means we are not having any friction. We are considering that we don't have any gradients of thermal conduction present over here. So it means we have nothing but the, because conduction term we have neglected in our energy equation. Okay, so it means I am considering that I don't have even the diffusion of heat, diffusion of momentum. So it means this is nothing but a reversible situation, and at the same point of time for this flow we have not considered any additional heat addition and heat removal. Okay, so what I can say that when I am defining this dp by d rho over here, this term actually I am defining nothing but for a isentropic situation. Is this point clear why I am saying this? Because I have not included conduction term in my energy equation, which says that I don't have diffusion of heat, so no gradients of temperature are present. And then I have considered inviscid situation, which tells that we will not be having friction and other dissipative effects for diffusion of momentum. Okay, and we are not doing any external heat addition and heat removal over here. So this is the reason that my situation is reversible adiabatic, and this is nothing but an isentropic situation over here. So what I can do, I can tell that in place of dp by d rho, I can write this as del p by del rho corresponding to constant entropy times d rho by rho equal to minus of v dv. Okay. Now, do you remember from our earlier discussion what is this p by rho, del p by del rho at constant entropy? What is del p by del rho at constant entropy? So if you recall from our very initial lectures, del p by del rho at constant entropy is nothing but equal to square of speed of sound. Because we have seen earlier that sound wave, propagation of sound wave is also nothing but an isentropic process. And if I relate variation of pressure and density, particularly for the case of a sound wave, means for isentropic flow situation, that was coming out to be equal to a square speed of sound. This we have done in the very initial lectures. So from here I can write a square is equal to a square into d rho by rho equal to minus of v dv. So from here I can get that d rho by rho is equal to minus of v dv by a square. Okay, now what will I do? I will multiply and divide this right hand side with v. So this will become minus of v square by a square into dv by v, and this will become minus of Mach number square into dv by v. Say this is my equation number 8. Okay, now if I substitute equation number 8 into equation number 7, then I can replace d rho by rho. So now I can write in place of d rho by rho as minus m square into dv by v plus dA by a plus equal to 0. And from here I will get simply that dA by a is equal to m square plus, sorry, m square minus 1 into dv by v. This is the important relation which is known as area velocity relation. So I can say that fundamentally when I have relationship in between area and velocity, that is a function of Mach number. Okay, so Mach number is getting involved over here. Now let's try to analyze this situation for different values of Mach number. So first situation, consider that my Mach number is approaching to 0. When my Mach number is approaching to 0, corresponding to that, I will be finding that dA by A equal to minus of dV by V. Okay, and ultimately if I do integration, this relation will be AV equal to constant, A into V equal to constant. So this is nothing but fundamentally my continuity equation for incompressible flow. Fine. You see the combination. When we consider our situation to be incompressible at low Mach number, when our Mach number is low, we say that our flow is nothing but incompressible flow. Okay, so you can see over here. So when our Mach number is approaching to 0, area velocity relation is giving me that A into V equal to constant, which is nothing but continuity equation for the incompressible flow situation. Okay, so this is one point. Then let's consider second situation when m is less than 1. So when m is less than 1, then I will be finding that if my, so for value of m, say less than 1 and greater than 0. Okay, I should not write equal to, because m approaching to 0 we have already seen. So now for value of m from 0 to 1. So for value of m from 0 to 1, I will be finding that this quantity m square will be always less than 1. So for this range, my m square will be always less than 1, and ultimately I will be finding that my dA by A will be having negative of dV by V. Is this point clear? For range of m from 0 to 1, based on the compressible flow nomenclature, I have nothing but subsonic flow. So I am referring this situation to nothing but the subsonic flow situation. So you can see that your area variation is equal to minus of velocity variation. So it means that for subsonic flow situation, the relationship or the variation of velocity and area will be opposite. So it means that if you have some situation where you are actually, what is happening here? Area is decreasing. So when area will be decreasing, your velocity will increase. So this will be direction of V increasing. And when your area is increasing, corresponding to that, you will be finding that your velocity is decreasing. So this is applicable for subsonic flow when your Mach number is between 0 to 1. So for a subsonic flow, if I decrease area, then my velocity increases, and if I increase area, then my velocity decreases. Is this point clear? Now let's take the third point, which is m is greater than 1. So if my m is greater than 1, then m square will also be greater than 1, and I will be finding that dA by A will be approaching to positive of dV by V. So velocity and area will be having variation in similar fashion. So it means that if for any situation my area is decreasing, so here V will also decrease, and if my area is increasing, then V will also increase. Is this one clear? So I have V decrease and V increase. So this is for case when m is greater than 1, and that is the case of a supersonic flow. Okay. Fourth situation, when my Mach number is equal to 1, corresponding to that I will be finding dA by A is 0. So if differential of area is becoming 0, it means either I will be having area as constant, either it will be minima or it will be maximum. So maximum, we don't have any limit for increasing area. So maximum it goes up to infinity. So it means I will be having some minima in area corresponding to m equal to 1. Okay. So let me explain how this can be actually justified. Say if I take a converging diverging nozzle. Okay. So if I take this type of section, this is called as converging diverging. At the moment I can call it as duct only. So this is my converging diverging duct. If I start with subsonic situation m less than 1, what will happen? Area is decreasing, so my velocity will keep on increasing, and at some point of time, if velocity is increasing, my Mach number will keep on increasing. At some point of time I will get a situation where m equal to 1, and after that what will happen? M will be greater than 1, and if area is increasing, then m will keep on increasing, because after this now I have a supersonic situation. So for supersonic flow situation, if area increases, velocity also increase. So I will be having here Mach number greater than 1. So this is the situation of a converging diverging duct. So if in a converging diverging duct I start at subsonic situation, then I am allowing first flow Mach number to reach sonic condition, and after sonic condition, then if I have to go to supersonic situation, then I have to increase the area. So you can see that before this Mach number 1 also my area is larger, and after this Mach number 1 also area is larger. So I am getting only a situation where area is minimum, that is corresponding to m equal to 1. Okay, so this is actually minimum area, and this is called as throat section. This is called as throat of the converging divergent section. Okay, and this physically also, whatever argument I have made over here, that corresponding to m equal to 0 I will be only having minima, that is also now we are able to prove. Okay, because so this is the case of nothing but isentropic, because flow situation is isentropic. So this is the case of isentropic expansion. So this is the case of isentropic expansion of a gas. So during the isentropic expansion of a gas, if I start with the subsonic situation, then I can actually increase its velocity to supersonic situation if I pass it through a converging diverging duct. So over this, for this situation, because this converging diverging duct is increasing the velocity of the flow, it is changing its velocity from subsonic to supersonic situation, I can call this as a nozzle. So in this case it is behaving like a nozzle over here. Okay, and if I take the reverse situation, if I take the reverse situation, say I am starting with Mach number greater than 1. So if I start with Mach number greater than 1, when my area is decreasing, my Mach number will decrease. It will reach a sonic situation at m equal to 1, and further when area is increasing, further there will be decrease in, because now I am moving towards the subsonic situation. So I will be having decrease in. So here Mach number will be less than 1. So this I can say as nothing but the process of isentropic compression. This is an isentropic compression, and in this process, if you see what I am doing, basically I am starting with a supersonic situation, and then I am actually decreasing its velocity. So this is nothing but this device is identical to that of a, so this is acting as a diffuser. Okay, is this one clear? Now important point is this area velocity relation, whatever we have seen over here, this area velocity relation is a very generic relation at the moment. Why it is generic relation? Because till now we have not imposed any condition of calorically perfect gas over here. Okay, so it means that this equation, this relation at the moment is applicable for calorically perfect gas, thermally perfect gas, reacting gas. For any type of gas it is actually applicable, because at this point I have not imposed any condition. Another important aspect is that mathematically, if I see, mathematically I have not imposed any approximation to drive this relation. So mathematically this is an exact relation. So mathematically if you see, this is an exact relation. However, physically we have imposed the condition that flow is having variation only in one dimension. Okay, so that is our physical imposition. Okay, not the mathematical imposition. Is this one clear? So this is one important aspect, that first is it is a generic relation, because still this relation we have not imposed any condition which is applicable for any specific type of fluid. Okay, and second point is mathematically, if I see, mathematically we have not taken any approximation, we have fully followed the exact solution. So that's why mathematically it is an exact relation. However, if we physically see, physically we have imposed the approximation that our flow variation is only in one direction. So physically we have the approximation for the physical situation where we are applying this mathematical relation, or even to derive this mathematical relation, physically we have imposed some approximation. Is this point clear? So now you can see that within a same convergent divergent nozzle I can also achieve isentropic expansion. It means it can work as a nozzle, and I can also achieve isentropic compression where it can work as a diffuser. Okay, so this shape is actually very important, and this particular shape you can see in your rocket engines, wind tunnels, etc. So how this shape is related to different applications, that I will discuss in the next lecture, and now I'll stop at this point.